So,
Could you like go over a
so
question?
say it.
Could you go over a question because I did the 2024 exam, I think it was.
Yeah,
And I, like with some help and everything, I was able to do it, but I can't find any more like examples or questions. So I don't know if I actually know how to do it.
yeah. Yeah. So those are kind of somewhat separate things. So a star essentially is if so, I'll just go back to. So if you look at uh just kind of the usual Dijkstra, right? The only so if you understand Dijkstra, you understand a star because the only change between the efficient Dijkstra and a star is this line, right? So ordinarily what we do with Dijkstra, let me open the slides.
I feel like Dijkstra is also something that's a little iffy.
Right. So I think that's kind of the right order to go. So So here's kind of the basic here's the basic idea with kind of the if with the efficient Dijkstra.
Yes.
This is actually a star. So we keep exploring. So to explore a node means that we visit it. So we're printing things out. We print it out at that point. And then we also add all of its neighbors as we're visiting it to the priority queue. The priority queue is the queue of all the nodes to be visited. Does that make sense? So the priority in which we visit the nodes is the sum of the shortest path from S to U, where U is the node that we're visiting right now, plus the edge from U to V, right? So we have this queue of all the nodes to be visited, right? And we sort the nodes by the sum of the distance from the source to the already visited node plus the edge from the node that we're currently visiting to this node V. So the node V that's to be visited could be added to the priority queue multiple times with different distances. Does that kind of make sense?
Yes.
Okay.
Okay, maybe because when we've done it, we've always done it in Python,
Yeah.
but um I'm kind of like struggling. How would you, even like from the examples, how would you put like something like a sum? How would you put it into a priority queue, and then how would the actual implementation work? I think
Yeah.
I need more examples to actually understand it.
Yeah. So I think kind of examples is maybe the wrong way to think about it because it's just the one algorithm, right?
Right.
But so it's not so much like examples as there's just like the one thing, right? So so let me go through the implementation that we used, right? So have we start with saying the node that's to be considered is is the start node, right?
Yes.
And the distance from start to start is 0. So that is what that means,
Okay.
right? So then what we do is we keep getting the node that's next in the priority queue. So that's this line. Right? So what we get is the distance from the kind of the distance from the source to this node, right? And the node itself. And we get it from the priority queue. So this is taking care of recording the previous node. Here, what we're saying is, okay, so we are visiting current. So that's now visited. And also for every neighbor of current, we add the neighbor to the priority queue. So the way we add it to the priority queue is we say, okay, so we add this node, and the priority is the weight of the edge from current to the node that's connected, plus the distance from source to from the start to source.
Okay, can you like repeat? Where do we actually declare what the weight is and what the distance from the start is?
Over
Okay,
here, right? So here we're saying, so this is the priority queue.
Yeah.
And we're saying add this content, and the priority is this much.
But they don't know what weight actually is. Like weight could be 3, weight could be like 0.2.
Yeah, it's a variable, yeah.
So we never say what it is.
Well, no, in the sense that we read it from the data.
So then how does Python know to read it from the data?
So let's maybe do kind of a concrete example. So here you have like the concrete data that's this graph, right? So
Yes.
so we have our queue, and we have our visited. And initially the visited is just nothing, right? And we're saying I'll add a with a distance of 0 to the queue. Okay. So then what we're doing is repeatedly right? So okay, does that make sense?
Yes.
Okay. So all right, so that's what we'll do. So we pop A from the queue. So the queue is now momentarily empty, and A is visited. And then the queue becomes B with priority 2 and D with priority 6, because those are the neighbors of A. So the nodes that are directly connected to A.
So we're using, I think, like depth first traversal.
No, this is
Okay.
digest.
Oh, okay.
And then we also have C, that's 1. Okay.
Yes.
So, all right. So then we say, okay, so again, kind of done with this iteration, get
Wait, I
C
have a
from,
question.
yeah.
Sorry. Two things. When you're pushing like if you're at A and then you pop it, so then it goes into visited. My first question is how do you know how do you like put what you pop because it's like gone now, I guess. How do you put that into visited? And then my second question is when you're pushing the neighbors into like the queue, how does how do you know like wait, how does the program know to also get the weight? Because the weight is
I-
like
Okay, so let me maybe do a different example. Maybe that will help answer your question. So, like in general, the answer is like it's just in the data, right? So let's say that they have like a linked list that's like this. So this would be just kind of like the easiest linked list. Okay, do like that's it, then do the weights. Guess we'll do connections. Just 1 second. I'm just trying to figure out a simple example. I guess we'll do. So something like this, right? So this represents this kind of linked list. And the weight here is like 10 and the weight here is like 20. Does that make sense?
yes. So then are we
Okay.
kind of creating it like a tuple?
Say again?
Are we creating it like a tuple?
So not really. So we have those 3 node objects, right? And each
Oh,
node has a next.
I
So
get it.
it's like it. So for example, like I'm connecting node 1 to node 2, and then I'm also specifying that the weight of the next connection is 10.
So you're making it like a struct in C.
Yes.
Got it.
Yeah. And then like let's say that what I want to do is compute the sum of all the weights of the edges, right? And the way I would do it is I would say like S is 0, and I'll start with node 1, and then I'll say, while current is not none, I'll add the weight, and I'll advance current to current.next, right? So I think this kind of has the same kind of question that you were asking, right? Which is, what is the weight? How do I know where the weight is? And the answer is, well, like I just read it off here.
Okay.
Does that kind of answer your question?
Yes.
So So it's the same here, right? So I just keep going, and in the same way that I got the weight there, I get the weight here from the connection. So the difference is in the linked list, there was only one connection. In a graph, there is each node is connected to multiple other nodes.
Okay, so just to clarify, because I also know, I think like the 2010 exam or something, had that. A graph is basically a bunch of linked lists, except they also have like levels on top of them. Or
Uh,
is that like something that
you
we
can
just made?
think about it that way. So there's two kind of levels there. So a graph is just like a bunch of nodes that are connected. And then you can represent the graph in different ways. So what you're talking about is kind of what we call the adjacency list representation of a graph, but that's not the only way to represent a graph.
Okay.
So you're right that you could implement a graph that way, but that's not the only way, right? So the other way that we talked about is so that is probably in graphs 1. Yeah. So so what you're talking about is adjacency list. So this kind of thing, I think that's what you're asking about, right?
Yeah.
And
Okay.
yeah, like you can think about it this way, and that is the implementation that we just saw. But you can also think about it, for example, as an adjacency matrix, right? Where the way you represent it is as this matrix, where if there is a connection, and in this case it's weighted, so if there's a connection between node 1 and node 0, then you represent it this way.
Okay. Got it. Kind of on that note, because I was looking back at like I was looking back at my notes
Mhm.
for I think like that extra and everything. And you said, or at least I think, you said that we won't really need to know it for the exam. Is that correct? Or did I like miswrite something?
Um, I don't know. I don't think I said that. No.
Okay. Okay, maybe I was like thinking of something else then.
Yeah.
Okay, cool. And oh, one more question. If no one else has a question. How does like AI or like face recognition and things like that work when you have to compute them?
Uh, so that's kind of a very general sort of question. So and there's kind of the answer is in practice, there's multiple ways of doing it. So as far as this class is concerned, we have, a small set of algorithms that we discussed, right? Uh, so specifically when you're talking about face recognition, okay, it's over here.
I think I'm also asking more in terms of like the exam
Mhm.
because we haven't really computed anything.
So we haven't, but the reason we haven't is that it's kind of trivial to do, right? So and kind of it depends depends on the input that it depends on the format of the input, right? But essentially, if you have some kind of representation of the x's and the y's, right? So for example, I might so kind of in the easiest kind of situation, you would just say it's a dictionary, right? So you have like faces.
and then it's kind of, so the zeroth face is so whatever, like maybe they're very small, right? So just like 4 pixels. So this, and then you have like something like this. And then the second one would be something like this, and so on, right? And so on.
Wait, why are we repeating Paul and John?
Well, I mean, like there could be multiple, we'll change this a little bit. So there can be like multiple pictures of Paul and multiple pictures of John, right?
Okay, got it.
And then you have like a new X. So that would be whatever, like 100. And then like the simplest thing you could do is just like compare it to every one of the pixels and find the label, right? So find so, yeah, so like something like this.
So I'm like thinking back to like project 3 right now where I
Mhm.
remember we had to do cosine similarity.
Yeah.
And I remember you mentioned that in class, but is that like the only way? Or is it just like I don't know.
So I mean, it's kind of so here there is like so here I defined the distance differently, right? So instead of doing cosine similarity, I defined the distance as the Euclidean distance, right?
Okay. So then are we like kind of required to know all of those? Like the cosine similarity or like the Euclidean distance and everything?
So I mean, I would assume that people know about the
Well,
Euclidean
yeah.
distance. So the cosine similarity, like I would not ask you for the formula of the cosine similarity.
Okay.
I would assume that kind of conceptually people know kind of to the extent that we discussed in lecture. I would not like ask for like the recall of the cosine similarity formula. I would ask, like I would expect that people would know about dot products and, like Euclidean distances.
Okay. Okay,
Right.
so that's basically how it works. You kind of like you basically just need to define a way to like compute some type of metric and then you
Mhm.
compare to find which one's the closest to
Yeah.
that. Okay, cool. Got it.
Yeah. Sorry, give me just 1 second. Yeah. Sorry, just 1 sec. Sorry, just give me a minute. Yeah, okay. Yeah. Sorry, you were saying?
Okay, no, wait, that helped quite a bit.
Okay.
Yeah, that clarified my question.
Professor, can I ask a quick question?
Yeah.
So is X here like part of a training set, or is it just an input and we're like we already
X
have
would be there. So the training set ordinarily would be something where you have the full information, right? So something like this where you have both the expected inputs and the expected outputs. Here the task is you have X that doesn't have a label, and we want to assign it to we want to assign a label to it. So that would be ordinarily referred to not as in the training set.
Okay, thank you. I also have just another question. This is like from like one of like the early lectures,
Mhm.
but so const car star versus car star const.
Okay.
Const car star, you can't change the values at the addresses, but then car star const, you just can't change the address of the pointer, or like the address at the pointer. Like you can't change the value of that
So
pointer, I
you
guess.
yeah. So the last one is the good way of saying it is you cannot change the pointer versus you cannot change the contents at the pointer.
Okay, thank you. I just have one other question.
Mhm.
It's in the slides, slide 48, actually. Could you explain like what the comments at the top on the left mean?
48.
48, yeah.
Yeah. So in the Python memory model, right? There is no passing the value. It's always the case that what you pass is the address, right?
Right.
So what we mean by something like so if you're doing something like this, right? So what happens is the address here gets copied to the address here, and that is why when you say L at 0 equals 5, this changes to 5.
Right.
Right? And that's the same with it's the same with integers, right? So if you say something like this, then that's the same structure. It's just that you now assign a new thing to the local variable L over here. Hello, right? So that is why if you say have a seat, please. So that is why when you say geoval, the global L doesn't change. It's not that the structure of F and G is different. It's just that what G does is different. It changes. Okay, I'll include you in the conversation as well. Oh, okay. Yeah, makes sense. So it might be that the sound is not going to be exactly synced, but yeah, yeah. Right. So the structure here is the same, and the
Okay.
structure with integers is also the same, right? So if you do something like this, in fact, like you could say this as well, right? So it's always the case that what you're doing is you're copying the address of whatever you're sending here to here. It's just that in Python, there is no way to change the contents of an integer.
Right. Like there's no way to like dereference it, so to speak.
That's right.
So could we like just say like in general that like all Python variables are actually just pointers to like data in the memory table?
Yeah, I mean that's essentially what it is. They're called references rather than pointers, but it's like a very thin distinction, right? So
Okay.
like the distinction between and like they're even not quite references either, but like references is closer, and the reason is like we don't have like asterisks or anything.
Okay, thank you.
Professor, can I ask a question about one of the previous exams?
Yeah.
Okay, so you know, for 2024 question 6,
I did.
where it says it's the race to 21.
Yeah,
like the
I
multiplied
know.
tertiary.
Yeah.
Yeah.
I was gonna say, except if it's 2024 Q6, because I'm just gonna do a separate video about it.
Oh, okay.
But go ahead. Like,
Okay.
so like I'll defer to like a video that I'll do this afternoon if it's just like please solve it. If you have a concrete question, I'm happy to answer.
Okay. Well, I tried solving it, but like
Yeah.
I don't know if I'm solving it like using like a true DFS approach,
Okay.
because like do you have to actually like make a graph
No.
like you would? Oh, okay.
No, so
Okay.
or at least kind of the way I thought about it. Like, to be honest, they should not have like putting that question there was just like a mistake.
Oh, okay.
But
Because
so yeah, like we accepted basically anything that worked.
oh, okay. Because I like I didn't even like use a queue or a stack. Like I just did it
Yeah,
like
well, so like
iteratively.
so part B tells you that if you used recursion in part A, then you have to not use recursion in part B. And that kind of means that you have to use a queue. Sorry,
Oh,
a stack,
okay.
I mean, yeah.
Okay.
Because like if you don't use recursion, then you do have to use a stack, right?
Okay. Okay, that makes sense. And then well, am I allowed to ask about question 7, like the A
Yeah.
star one?
Yeah.
Okay. So
Oh, question 7 is like the continuation. Yeah.
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 Like, are you also gonna cover that in the video or?
Yeah. I'll just solve both of them. Yeah.
Okay. Cause I like didn't know if I was doing it right. I kind of just like took the skeleton of the solution that was given in like one of the slides and I try to
Mhm.
solve it like that.
Yeah.
But
Yeah, it's like it's a little bit tricky, which is why I kind of like I want to just make like a short video, and like I need to like prepare for like 5 minutes before I make it. So and, like that's why I'm deferring. But I promise that like after this call, I'll just make it.
okay, sounds good. Also, just like a general question, you know, like those really long questions on the first midterms that were like, oh, you take in a file and then like you read the file and then you like do something with the file contents.
Yeah.
Is there gonna be a question like that on the exam? Because like I was looking at the previous ones and they usually didn't have one.
Yeah.
But
I mean, like there's no usually because there's just 3 of them.
okay, that's fair. Yeah.
But like so and I think like so I will say I guess 2 things there, right? So one is that 2021 was special both because it was my first time teaching that course and also because it was done online, right? So that's I don't exactly recall what we did in 2021, but if you're asking about that, then that's part of it. But also, I think you actually see quite often things that are kind of a scaled down version of Project One, right?
Okay.
So that kind of thing, like for sure, like it actually, like I think has done it several times on like previous midterms, previous exams. Certainly, like it wouldn't be, like I also tried to mix it up a little bit, but it's certainly like legit, like just like it was legitimate to ask about scaled down version of Project One. Previously, it's still legitimate, right?
Yeah, that makes sense. It's just that like those questions usually end up being like quite long. So I was wondering if they were gonna have one.
I mean, like, look, everyone's gonna sit there 2.5 hours, no matter
That's
what.
fair.
So,
Yeah, that's fair. That's fair.
yeah,
Okay, thank you.
yeah. Yeah, so there's also a person who's in person. Does anyone? I think I've spoken to everyone who's online now. So do you want to ask?
Okay, sure.
Okay.
First of all, will that be on the exam? And
No.
if so, okay. So should I try to understand the proof if I want to understand the algorithm, or is it?
I mean,
if I just understand the algorithm?
if you understand the algorithms, you do not have to understand the proof. However, I'm happy to talk about it.
Could you talk about the?
Okay. So okay. So where is that? Right. So let me kind of recap what. Oh, there's like a bunch of comments. Chat. Yeah. Okay. So yeah, so to recap what we're doing here, right? So we start with just the source, and we're saying this distance from the source to the source is 0. So d of v is like the shortest path from the length of the shortest path, right? So then what we do is we say, let's look at
Just sit there, 'cause
Yeah,
there's a
yeah,
delay.
yeah. So you can also join on Zoom where there probably isn't a delay, but anyways, so what we're doing with Dijkstra, I'm sorry about that. Just put it on the floor. It's fine. So so what we're yeah, sorry about yeah.
Yeah.
So what we're doing with Dijkstra is we're saying look at the gray set. So the gray set is everything that's been visited. And then look for an edge from the visited set to something else, such that the distance from the source to inside the set plus the edge to outside is as short as possible, right? So if we're thinking about the visited set that's S and X and U, then the options are either S to X, X to Y, or S to U, UV. Right? And then we take whichever one is the shortest.
Explain even like after choose V in big V.
Yeah, so yeah, so we're saying choose V from everything. So V is all the nodes, and S is the visited ones. And this is everything that's in V but not in S, so not yet visited.
Oh. So. If it's not visited.
Yeah.
Such that. So distance.
So the distance to U plus the edge from U to V is as small as possible.
How do you? I'm still having trouble understanding like that part.
Okay, so D is our distances that we have recorded so far, right? So we start out not knowing the distance to anything. So by distance, we mean the length of the shortest path. And then we keep updating D, where if we say, set dv to whatever, that's already set. So Dijkstra's is a way of doing it that makes it so that this is the actual distance. So the proof is about saying, if you follow this procedure, then when you record d of v, it's actually the correct distance. So we haven't proven it yet, but that's like the algorithm, right? The way the algorithm works is we're saying you have the visited set, so the set for which you recorded the distances. And then you're saying, okay, like what should I visit next? Where if I visited it, I will have known what the distance from the source is, the distance meaning the length of the shortest possible path. So the way to do it using Dijkstra is to say we are selecting an unvisited node such that the distance from S to U inside the visited set plus the edge from U to V is as small as possible.
Okay.
Right? So out of all the possible ways of going from inside the visited set to outside the visited set, this is the shortest one. Where this is an edge, this is possibly kind of multiple edges where you go from S to U. Okay. So the idea is if the way you're doing it is you keep adding edges in this particular, keep adding nodes, sorry, in this particular way, then you will have recorded the correct shortest paths. So all the proof is saying is that if this is your situation, and if S to U plus UV is as small as possible, then there is no shorter path than from S to V through U, right? And the reason is, well, like, what are the other possibilities? So what I'm going to say is the proof, right? So what are the other possibilities? Well, the other possibilities is you go from S to somewhere else inside the visited set, maybe to X, and then maybe there is an edge from X to V, and maybe that's shorter, but that's not possible. The reason that's not possible is we specifically selected V such that S to U plus UV is as short as possible. So even if you could go from S to X and then from XV, that would be shorter. That would be longer, sorry. So that's not possible. The other possibility is, well, like maybe you could get to V by going from S to somewhere in the visited set, and then jump somewhere outside the visited set, and then go from there to V. But that's way longer than from S to U plus UV, because from S to any X plus XY is already longer than from S to U plus UV, because if from S to X plus XY were shorter than from S to U, UV, then we would have visited Y instead of V.
Then it would have been inside.
That well, and no, it would not have necessarily been inside, but we specifically selected V such that S to U
Yeah.
plus UV is as short as possible. So it's definitely already the case that from S to X plus XY is already longer than from S to U plus UV. So for sure, from S to X, XY, from Y to V is longer, because getting to Y is already more expensive.
Okay. So there are basically just three cases. So the first case is, you said the shortest case, which is from S to U and then U to V, and that is assumed or like defined to be the shortest one.
Well, it's not so much that it's defined, it's that we specifically select V such that this is as small as possible.
Is selected. And then you could also go other ways, which is like S to X, and then X could also go to V,
Right.
but that's not the shortest path.
Right.
because That's not what we have selected.
Yeah, that's right, because like if it were the case that S to
Then-
X plus XV is shorter, then that's what we would have used, rather than
Then it
S to U plus UV.
And then the other case is S to X and then X to
Y.
Y. But that's already longer than what we already
Exactly.
have, so it's can't be the shortest.
Exactly.
Shortest path.
Exactly.
Oh, okay.
Yeah.
that's fine. And then I also didn't understand the complexity
Mhm.
part of shreds.
Okay. Yeah, so the complexity is a little bit difficult because so like if you just look at this algorithm, right? So how do you do this, right? So here you're saying choose a V such that this is as small as possible, right? So one way to think about it is, well, like, how do you choose a V? Well, like, try all the possible Vs and see for which one is this guy as small as possible, right? So if you do this just in a straightforward way of like keep adding nodes to the visited set, and every time you select which node to add next, you just look through all of them. That's going to be basically all V squared, right? Because this in the worst case, this is you just go through you just visit all the nodes, and then here, depending on how clever you are, like at best, what you would do is initially look through all n nodes, and then through n-1 that were not visited, n-2 that were not visited, n-3 that were not visited. That is 1 plus 2 and so on plus n. That's all n squared.
Oh, okay, so you get O of n squared from the from how
Yeah,
Okay.
yeah. So so that is kind of the naive way. And then like if you do it with the priority queue that's fast, right? Then what you could say is, okay, so pop and push is log v. Then you can say, so do you want me to go over like the transformation to the priority queue thing?
Yes.
Okay. So so the basic idea here is, okay, like rather than kind of just look at all the neighbors of everything in the visited set and select the neighbor that's the best, what we can say is when you visit, for example, you can say, okay, like I'll add all of U's neighbors to the priority queue. And the priority in the priority queue would be the distance of getting from S to the neighbor, so to the neighbor V in this case, from U, from the node that we just visited. So one alternative is I just look at all the possible edges from inside the visited set to outside the visited set every time. The other alternative is, as I visit a node, I say, I might like to go outside the visit set through this node. So I'll just keep a record of all the neighbors of the nodes that I visited. And I'll also remember what would be the distance from S to U plus UV for every neighbor. Right?
Is that similar to memoization or not?
I think it's kind of like a little bit analogous, yeah, and like in the sense that so it's different in the sense that you're not exactly so you have potentially multiple entries for V, right? So with memoization, you're just saying, oh, next time I try to get the answer for V, I know the answer. Here, it's not exactly like that because it might be that you add another, so maybe you visit Y at some point and Y is also a neighbor of V. And you'll say, well, like if I go through Y to V, I'll keep a record of how long that would take, right? So for a single potential node, I could have multiple entries with multiple ways of getting to that node.
Whereas the memoization is only one.
That's right. Yeah. So for yeah. So it's and like you can code things kind of different ways as well. So it's not exactly memoization, but it's a similar kind of thing. So the other difference is that so specifically for priority queues, there is a way of being able to quickly get the minimal element. And that's kind of exactly what we want, right? So I want to say I have all those potential nodes to be visited, and I have the associated distances. And I want to be able to get the node with the smallest potential distance from the source to that node, because that's the thing that I want to visit next, right? Is that kind of making sense?
Yeah. So
Okay.
just to make sure that I understand.
Mhm.
So for all the nodes, you keep track of all the distance to neighboring nodes from that node?
No, so the total distances, right? So from the source to the neighbor, to the potential node to be visited. So when I visit U, I say, oh, if I want to visit V through U, then it would cost me the distance from S to U plus the edge UV.
So the total distance.
Yeah.
From one node to all the possible nodes.
To all the neighbor nodes, right? So I visit U,
Yeah.
and then I say, well, I'll put V in the queue with the priority, the distance from S to U, plus the edge UV.
How come neighbor of S?
V is not a neighbor of S. V is a neighbor of U because there is an edge between U and V.
So why are you looking at the distance from S?
Uh, Yeah, I am. Yeah. So because that's what I eventually want to compute, right? So my goal is to compute the distance from S to everything else, right? And then the big issue is that, well, I don't know what the distance from S to V is, because maybe there's multiple ways of getting from S to V, and one of them is the best, but I haven't explored all of them. Right? So what Dijkstra says is if you visit the nodes in a particular order, and then you record the distance as, if you're adding V and you're saying I want to use UV, and then S to U plus UV is as short as possible, then we know that it's true that the distance from S to V
Is the shortest.
is the shortest. Yeah. So the strategy with the priority queue is just saying every time I visit a node, so let's say I visit U, I'll also keep track of a possible way of getting from S to V is through U. And the distance that's associated with that is S to U plus UV.
Oh, okay.
Right? So, and then the priority, so the reason this is more efficient is that there is a way to implement a priority queue so that it costs O of log n to pop and O of log n to push. So it's easy, meaning cheap, to extract the next node to visit from the priority queue. Like essentially all you're doing is you're saying like, I will eventually need to say which node to visit next. So instead of just like going through all the nodes that I could potentially visit every time and selecting the one such that, du plus uv is as short as possible, I'll just record, if I want to get to v, it's going to cost du plus uv in my priority queue. And then I'll say, okay, like what do I get next from the priority queue that's the cheapest? That's what I'll visit. Okay, so it's still the same idea. It's just that every time I visit a node, I record what it would cost to get to the neighbors of that node through that node.
So, sorry, could you repeat the last sentence? So
every time I visit a node, I record for each neighbor of that node how much it would cost to get to the neighbor through the node that I'm currently visiting.
Oh, okay. Each time you visit a node, record the cost from that neighbor to the node.
From the source to the node. From the source to the neighbor.
To the neighbors.
Yeah, through the node. Yeah.
Also, this might be a stupid question, but what is the difference between priority queue and like the normal queue?
So a priority queue, the operations are get the so specifically with like min priority, get the element with the lowest priority. A normal queue is first in, first out.
Yeah.
So kind of
So
get the element that was inserted, the longest time ago. So kind of the commonality is you can push and pop into both. The difference is the order. So the order in which you get the elements from the priority queue is determined by the priorities. The order in which you get elements from a normal queue is when were the elements inserted.
So for the priority queue, would you have to sort like
that is one way to do it. That would be kind of slow. That is one way. That is one way to do it. Is you just keep all. So when you insert, you just insert so that it's sorted by priority, and then it's easy to dequeue, right? So because to dequeue, you just take whatever, like the last element or the first element, depending on like whether it's sorted in increasing or decreasing order. The problem is that inserting into that is O of n, because you need to find where to insert. Well, like finding could be log n, but you need to move, like if it's an array, you need to move all the elements, or if it's a linked list, then it's expensive to find the place, because then you cannot do binary search in a linked list.
So what would be the faster, like more efficient way?
Yeah, so we haven't done it this semester. So the usual way people do it is with something called a heap. We just kind of haven't gotten around to actually implementing it. So there is like yeah, we just haven't done it. So there is a way to do it. There is also a way to do it with binary search trees, which we again have not gotten around to.
Are binary search trees on the exam? Because
They
I
could
think
be.
we did go over like.
So they are, to the extent that we went over. Yeah.
Okay,
Yeah.
okay. So we wouldn't be expected to implement priority queues using binary trees, or would?
No, that's very difficult.
Okay, okay, okay.
No, and we haven't done it.
Okay. I think that's it. For all
Yeah.
the questions.
Yeah,
I think makes
okay.
sense.
Cool.
Thank you.
Sure.
Professor, could I ask a quick question about structs and how we like when we make functions to create them?
Okay.
So would I be able to like I can just copy paste the code, but
Okay.
here. So the first function is something we did in lecture, and the second is just something I added to it.
Okay.
Or like the second function is like something I made. How come like when we're like if we have like a string within the struct, why do we malloc it? Like why do we like allocate a block of memory and then use string copy as opposed to just making that pointer equal to the pointer of the name that we input, like for a student?
Yeah, you could. The issue is that if you do it in the second way that you mentioned, then you have basically an alias string. And so what you're doing in V2 is you're making ps.name be an alias of whatever you're passing in, right?
So it's legal, it just provides like it causes dependencies basically.
I mean that. So also if it happens that you want to modify name, but you're not guaranteed that it's not actually a const, that might be a problem.
Like you're
Right.
saying if you don't want it to be modifiable.
No, so in here, so imagine that some other function modifies one letter in name, right?
Yeah.
So as far as the definition of struct student2 is concerned, that's completely legal, right? Because it's not a const car star name, it's just car star name. You're completely allowed to modify like name at 0 to something else, right?
Right.
But you're not guaranteed that that's actually going to work if it happens that actually the name that you passed is a constant string,
Okay.
which like would actually happen all the time, right? So like if you pass a string literal there, that
Yeah.
would be a constant. So you could say, well, like if that's your issue, well, I'll just say in the definition of student2, it's actually a const car star. And if that is the situation, then that is kind of fine.
Okay.
It could still be, so you still have kind of the aliasing problem. So if, for example, the name that you're passing into create student2 v2 was like malloced and then free it or something, then the student struct wouldn't know about it.
Right.
So like you can do it, and in some situation that's fine to do, but you need to kind of like there's problems with that.
Okay.
So whereas like if you just do strcpy, then you're obviously completely disconnected from whatever is the string that you passed out. You just copy it, but you don't care.
So you're eliminating risks basically.
Well, I mean, that. Now you could say, well, like the way I'll eliminate risk is I'll just like make sure that, if I passed in const car star, then I'll just define the name instead student two as const car star, and then I don't modify it. But that doesn't take care of all the risks. It's also a question of if you literally want to be able to modify the contents of name, then you just cannot, then it's obviously not correct to just say it's gonna be fine. I'll just like assume that the name that they passed is actually modifiable. If that makes sense.
Yes, it does. So it's fine to do it. It's just there's implications if you do it.
Yeah.
Okay. Okay, thank you. So like I guess like a lot of the stuff we do, like there's obviously like different ways to do it. Like instead of like using pointers, we could just like have return statements, right?
Yeah.
Yeah. Okay. Okay. That's basically it. Okay, thank you.
Sure.
Is it just like was it just like an hour long office hour and then you have another one later?
I mean, I never said it was an hour, but I think you're the last one, so it
Yeah.
would have
So
been.
I don't really have anything else for now,
Yeah,
but
okay.
I might
Okay.
be back at 6. Thank you.
All right. Okay. See ya. Bye.
Have a good day.